Today we are going to be looking at another popular problem from the Leetcode blind 75 list, and we're going to be solving the three-sum problem. To solve the three-sum problem, it's important that we go over the two-sum problem and the intuition behind solving it optimally in O of n time, because solving the two-sum problem intuitively would give us an advantage on understanding and solving this three-sum problem better. So the two-sum problem is a classic Leetcode problem that helps us get started with Leetcode solving. So initially you'll be given a list and a target. So you have to find two elements that add up to the target. You have to find two elements in the list that add up to the target and return their corresponding indices. So the brute force approach of two-sum problem is using nested for loops and try to solve it in O of n square time complexity, but a more optimal way would be to use a hash map as a lookup table and try to solve it in O of n time complexity. So let's see how we can do that. So if we have two numbers x and y adding up to a target t, then subtracting either of those numbers gives us the other number, right? So we can just work with pairs. So if we call this as a remaining element, then we return the index of this remaining element and the index of its corresponding pair, which would be our answer for this question. But to return the index of this remaining element, we have to store the index of its corresponding pair in the first place. So that's where using a dictionary can be useful to solve this two-sum problem effectively. So how does a dictionary help us? So let's go over these elements. So the first case, we would have 9 minus 2, which would be 7. Now we see if 7 is present in our dictionary. Since we are at our first index, 7 is not present in the dictionary. So what we do is, in the dictionary, we place this 2 as a key and store its index as its corresponding value. How does that help us? So when we move on to the next element, 7, then we would do 9 minus 7, which accumulates to 2. Now 2, whether is 2 present in the dictionary? Yes, 2 is present in the dictionary, so we can just return the stored index of 2 and the index of the current element. The index of the current element is 1, so that is our answer for this test case, which is the correct answer. So programmatically, we initialize our dictionary to be an empty dictionary. We traverse the list and find out the remainder, which would be the target minus nums of I. If remainder is in the dictionary, we would return something, but let's just store it first if it is not present in the dictionary. So is I, and if it is present, then we would return as a list the remainder and the current index. So this should be sufficient. We see that it is, so it is sufficient and it solves it in very efficiently. So how can we use it to our advantage for the three-sum problem? Let's just understand the three-sum problem first. So you are given a list of elements and you have to return all the triplets. By triplets, they mean all sets of 3 elements that add up to 0. So in a list, 3 elements that add up to 0, and you have to be careful that the indices of those three elements cannot be equal to each other. So if nums I, nums j, and nums k are your three elements, then I cannot be equal to j cannot be equal to k, and I cannot be equal to k. And your solution set must not contain duplicate triplets. That means that if your A, B, C is a triplet that add up to 0, then it can only happen once. That means A, B, C can be present only once. That's one. Another aspect is if ABC is a solution, then BAC cannot be a solution. That means you cannot have same elements reordered and returned as a triplet. So this cannot be a solution. Hence, all other possible combinations with ABC would not be acceptable as solutions. Okay, so now that we understand this constraint that the solution set must not contain duplicate triplets, the triplets should accumulate up to 0. Let's see how we can benefit from our understanding of the two-sum using a dictionary to our advantage here in three-sum. So in two-sum, we had two elements adding up to a target. In three-sum, we would have three elements adding up to a target. So let's just write them. So x, y, and z adding up to a target of 0. If we want to single out x, then we would need to have, I'm sorry for this, so let's just do this. Okay, so our remaining element is x, and we would sort of organize our dictionary. If x is present in the dictionary, then we would sort of mark its presence, and if x is not present, we'd include it in the dictionary. So let's just go ahead and try to solve it programmatically, and I'll try to explain at each step why I am doing certain things that I'm doing in the code. Okay, first of all, let's just say our resultant would be an empty set. Now, why our resultant would be a set? Because what we talked about earlier, this triplet, this cannot repeat itself, it can only happen once. Hence, we need to store the triplets as lists in a set. Then we need to sort our given nums list. Why do we need to sort it? That reason is already also there. If ABC is our answer, then BAC cannot be an answer, CAB cannot be an answer, BCA cannot be an answer. So the ordering of the elements in the triplet list cannot be changed. So if we sort the list in the first place, then whatever approach we follow rest of the way, you will see it makes sense that we are not falling into that trap of reordering the elements in the list and returning it. In this case of solving this three-sum problem, the main issue you will face is in the duplicate triplets, and there are many ways you can fall into the duplicate triplets trap. So for I in range len of nums, we initialize an empty dictionary. So let's just say dt for j in range I plus 1 comma. Now why do we start the j from I plus 1? So if we draw it out, let's say we have this n number of elements in our list, right? So our I starts at here, the element at I, let's just consider it A, right? So we need to find three elements, right? So let's just not call it A, let's just call it X, because we sort of used XYZ here. So if X is our element at index I, then the remaining is Y and z. This y and z finding should be done in our j loop. So since we are already at ith index where element x is present, element x is already part of a triplet. It can be a part of triplet, it cannot be a part of triplet, but it is being considered as a part of triplet checking. So why do we would not need y and z to be starting at x, because x is a different element, right? And we have already seen the constraint that I, j, k cannot be equal to each other. Hence the jth loop should always start at an index more than I. Imagine that if I is somewhere here, so is there any point in looking up y and z from the previous two elements? No, right? Because those two elements have already been processed as x beforehand, and their corresponding y and z are already found or not found if they are not in triplets. Then we don't need to again consider them as y and z, because their corresponding x was already checked. Hence we always need to start the jth loop at an index more than I. So for j in that, so now we will do this x checking. So x would be 0 minus nums of I minus nums of j. Now we check if x is in our dictionary. As usual, we'll write it later, this condition. So if x is not present, then we just do present or an absent checking for the element at jth index in the dictionary, because we are returning the elements themselves, so we don't need to bother about storing the indices, unlike the two-sum case. Okay, so if x is in the dictionary, then we add it to our set as a list. So that would be nums of I, your x, and nums of j. Okay, finally we would return. So you see that each triplet is contained in a list themselves, so we have to return whatever is present in our resultant set as an individual list. So list y for y in result. Well, it is solving it, but it's taking around 2.5 seconds, so there should be some ways to optimize it. Thinking about it, if you go back to our drawing board, if let's say we have an element 3, we have element -3 here and another element and -3 here. Do we need to process this -3 again? No, right? Because this element, if it is being considered x at an index I, then this, for this element y z is already checked. Then for the same element we should not check this y z again, right? If we check this yz again for the same element, we are just doing unnecessary computations and taking up a lot of time. So we can just continue and move on to the next I. So the way to do that is, if our I is greater than 0 and nums of I is equal to nums of I minus 1, we can just continue. Also, since we are sorting this nums list, one intuition that we already understand is that we have to find triplets that sum up to 0, right? So if any element at our list is greater than 0 and it's sorted in an ascending order, the list is sorted in an ascending order. Think about it. If some list is sorted in an ascending order and element is greater than 0, then all the rest of the elements are greater than this element itself, right? This one itself. Then there is no point in checking all the other elements. That's the another advantage of sorting. If at any element at any position is greater than 0, we don't need to check the elements occurring after it, because they will anyways be greater than that element which we are currently at. So what we do is, if nums of I is greater than 0, we totally break the loop, and we see that we had 527 milliseconds. That should be reduced now. Yes, so we narrowed it out to 803 milliseconds. So I gotta be honest, this is one of the tougher problems in Leetcode. So I do hope you guys spend more time on intuitively understanding why things work the way they do, and how you can use two-sum to benefit your case in three-sum problem, and even try to solve it in less time. If, for example, my case takes, for sorting it takes n log n, and the nested for loops take n square, so that is O of n square time complexity, and the space complexity would be O of n because I'm using a dictionary. And a set. So anyways, both of them accumulating up to O of n. So you can reduce the time and space complexity if you try to design in more efficient approach. If you guys come up with that, you are most welcome to do so in the comment section and let me know about my approach. Thank you, and I hope to catch you guys in the next one.